Yeah, thanks. So let me start with the organizational remarks about homework due dates. The first homework will be released today, and the due date is Saturday, November 21. Then we will definitely release the second homework in a week because, well, we will cover all the necessary tools today and on Friday. So we can even release it a couple of days before November 17 because, well, it's ready. As for the third homework, as I said during, well, the first lecture, we was not sure how many homeworks will be provided, 3 or 4. And so finally, well, we are slightly behind the schedule, and well, we have no room for the 4th homework. So we will have only 3. And the key question for me is what will be the content of this homework? Will we merge exercises from homework 3 and 4 or create something new? So we'll try to decide during this week and then finally fix the release date. It depends obviously on the content of the course and it's matching with the content of the homework. As for the final project, well, it will be at the end of the course. So we'll have 2 weeks to prepare the final projects and we'll have time slots and maybe not for lectures, but to one-to-one consultations with me, with TAs. And I will give more information closer to December. So this is the first one, and the second one is about this delay in our lectures. So according to the schedule I shared at the beginning of the course, this lecture should be on Friday. And today we will, again, the plan was that today lecture should be devoted to epipolar geometry. I decided that we can merge these topics, and actually these topics are connected. I mean, half transform and projective transform, and we can drop epipolar geometry because, well, it's not a really common topic, and it was a mistake at the beginning to include this topic to our introductory course. So I just like to say a couple of words about epipolar geometry. So what is it? It's about stereo vision. So for all our exercises and images we process, we assume that we have only one camera to collect the data. And in some cases, you have 2 cameras. For example, we have 2 eyes to see it in our human vision system, and the complex processing, device or set of algorithms within our brain. So epipolar geometry is about the way to describe, to analyze images which were collected using 2 cameras. And in particular, if you know some dependencies, for example, distances and angles related to cameras, we can say a lot about objects, their relative positions, as you can see from this example. So if you have only one image, you cannot say what is closer to you, the green ball or the orange one. But if you have 2 cameras, you can not only say which one is closer. For example, that from this camera, it's obvious that the green one is closer. But if you know both images, then you can extract a lot of information about position and size of your objects. And here is some, again, very brief illustration of this idea is that you have two cameras, and you know the distance, you know angles, and it means that you can extract some useful information from both images. So if you, for some reasons, if you work with stereo images, you need to go deeper to this topic by yourselves, and well, unfortunately, we do not have time for this. Actually, both times and exercises for this type of for this topic. Now, let me switch to, let me continue the discussion of patterns we can extract from images. So we already discussed that edges provide a lot of information about objects, but still, so we know methods to extract edges from our images, but then we need to somehow analyze edges. So right now, just a binary image, and it doesn't help us to create an algorithm to identify some objects within this image, even if we preserve a lot of information when we created edges, and we simplify our image significantly, right? So we started with a three-dimensional and three-channel RGB image, and then converted it to a binary one. And still, this binary image contains a lot of information. So my question is, imagine that we have this image or another image with edges, so a binary image. Which structures can we extract? So we know how to extract these structures from the image, and maybe we can suggest some useful structures we cannot extract right now because we don't know the methods to extract. Where is the chat? Oops. Find the chat. Where is it? Yeah. So please use chat to suggest something. We know at least some methods to extract well, structures. I haven't defined structures, but well, you can think that it's some simple objects or maybe even complex objects. Is it too early to ask questions at 9 a.m.? Yeah, lines. Well, lines is, this is a good suggestion, but right now we don't know how to extract lines. Today we, at 11:30, we will have a seminar, actually from lecture 2, maybe 3, related to template matching. And the exercise was to find lamps, and you can find not exactly the same lamps, but similar here. So you can use templates to find some objects. Yeah, the second suggestion is contours. Actually, closed shapes can be described as a subset of contours. So actually, yeah, we can find contours, and then we can process contours to find figures like, for example, squares or ellipses. So it means that we can extract something, and I'd like to highlight that template matching can be done using edges, and sometimes it's really a good choice because you have zero problems with different, say, illuminance of different parts of your image, with some missing parts of your objects with different colors. If you have a binary template, for example, a contour extracted from edges, this can be a good way to do template matching. Yeah, so contours to identify some simple figures, or templates to identify maybe complex figures, but with a predefined shape and position. I mean position in terms of rotation, because, well, obviously template matching is not robust to rotation. And actually, by default, template matching is also not robust to scaling to different sizes of your template and the actual object within your image. But this part can be fixed simply. You can just scale your template and repeat template matching several times with different scales of your template. But for rotation, you can try to do a similar algorithm, so to rotate by a random angle or by a predefined set of angles, but you will end up with a huge number of different results of template matching, and likely you will have a lot of false positives. So as we have suggestions from also Alexander, we can try to find lines. Also, I'd like to add that sometimes when I want to find corners, and we'll discuss this approach during the next lecture, I mean corners. And right now we will concentrate on lines. And we'll use half transform for this. This is not the only way, and I guess that we will we'll discuss other alternatives within our exercises mainly. But half transform is a tool to define lines and images, and actually lines can give us a lot of information. For example, we can extract some angles, or we can define some structures. For example, repeating structures as we have here. If we know lines, we can identify some patterns and say distinguish this pattern and this pattern. Half transform is quite robust tool and can be used even for noisy images. And in addition, it can be used for other types of objects, mainly circles or ellipses, but we'll discuss it a little bit later. Right now, let me start with this image, and oops, where is it? And my question is, the question was here, but it seems that I removed that slide or whatever. So my question is, can you define groups of parallel lines within this image? I mean, groups, groups of lines, some similar lines related to this house. For example, we have these edges of the roof, and we can say, well, that these two lines are such a group, or lines related to, well, it's not really, yeah, actually we do not have a lot of lines because we have these three here, and it's not really visible. Yeah, for example, we have lines. Yeah, we have words, and this is an image from from internet with these watermarks. Yeah. Um, I guess that we can define lines, for example, at least a set of vertical lines related to these parts of upper part of the building, right? We have several lines here. Also, we have lines, a set of horizontal lines for this wall of the building and for this wall. Do you agree that we can we can think we can analyze, for example, these two groups mainly. So lines for this wall and lines, horizontal lines for this wall. What is the difference between edges and lines? This is a question from chat. Edges, we define edges as well, a discontinuity or jump, significant change in image intensities. These, say, jump can be caused by different reasons. For example, by different illumination, or by shadow, or by physical edge within image, like we have here, right? We have an edge between a building and a background. Then we can say that edges can have arbitrary shape. It can be a line, or it can be like here, well, a set of triangles. It can be a smooth curve. Do we have an example here? Well, maybe not. Maybe this part of, if we can separate different trees. So edge, well, this is a more general object, and we want to detect straight line. Yeah, so line is just a line, and it can be. We have actually two different options. We can try to detect just a line without starting and ending point, or well, and sometimes we want to detect to identify these two endpoints. But well, this is connected problems. Is it clear the difference between edges and lines? Okay, if it's not clear, please ask one more time, and I try to explain better. And so my question is about these lines. So we have two set of lines. These lines, horizontal lines for this wall and for this wall. My question is, are lines within these groups, I mean both groups, are parallel? All lines for this group are parallel to each other, and all lines within this group also are parallel to each other. Obviously, they are not parallel between groups, but within groups, well, the most direct question is yes. Do you agree? So because we know that we have some building parts, and usually this can be in 2D, it can be described as kind of rectangular. So we know that we have parallel surfaces of these building blocks. So these lines must be parallel. Please answer in chat to agree or not. Yeah, a very good question from Lila. We we know from our experience, from our understanding what is the object. We know that these lines must be parallel. But when we create an image, actually, we cannot guarantee that all parallel lines, actually parallel lines, will be parallel on the image. And this is the illustration. Actually, this is a different image, and I didn't find the original, so I just added a random image from the internet. And here we have different sets of parallel lines which are shown in different colors. So for green lines, and this is vertical lines like we have here, these lines are actually parallel both in real world and here. Yes, for these yellow lines and purple, we see that we have a common point. So now these lines aren't parallel. And we have so-called vanishing line. And this is the line, I do not have this image here, but imagine that you stay on straight railways, and you see along these railways. And you'll see that, well, this vanishing point within your side of view. So here we do not see this vanishing point because due to well, the structure of these lines. But you can imagine that we have this point somewhere. And if we plot a set of different parallel lines, I mean parallel in real world, then vanishing points for all of them except these green lines, the vanishing point will be located somewhere on this vanishing line. And if you have parallel lines which are orthogonal to vanishing line, well, in this case, they will remain parallel even on image. What is the transformation behind this image? Why do we have this say effect? To understand this transformation, we need to discuss different types of linear transformations we can apply to every image. And this is actually the summary. And I propose to start from the bottom part because, well, this is the most simplest transformation we can do. These are names, and D or F means degrees of freedom. So you can think that this is the number of tunable parameters. And well, this is matrix form, as we saying that this is a linear transform. Anyone from the list, it means that we can just multiply our image as matrix by another matrix, and sorry, not an image, a vector, to identify new coordinates. So and we can do this to modify images, applying, say, to, well, not images actually. Yeah, if we have coordinates in in Euclidean space, then we can apply this linear transform to create, say, a new coordinate. The most simplest transformation is the Euclidean one, and we have only 3 parameters and 2 operations to work with. The first one is the position of origin, so we can shift the origin, and this gives us 2 degrees of freedom. And also we have the third parameter, rotation, related to rotation. So actually this is just an angle, but in matrix form it can be written in this way. And it means that if we apply this Euclidean transform, we preserve definitely length of all our lines and objects, area, etc., etc. So this is the most rigid transform. Then we can add one more parameter, and we can also scale our objects, our vectors. And in this case, we just add this parameter s, and we have 4 parameters. And as we can see from this example now, we cannot guarantee that the, say, area or length, so some sizes, will be preserved by the ratio, but the ratio of the lengths will be the same, just because we scale all the directions with the same scaling factor. And also the angles, all the angles will be the same, because we just scale in all directions or rotate. Then we can switch to affine transform. And if we apply affine transform, so yeah, actually I didn't say that explicitly. So we work with 2-dimensional vectors, and the last line is related to just free term or bias. Well, here we have affine transform. We now have 6 degrees of freedom, and in addition to this scaling in one direction, we also add scaling in different direction, and combining it with rotation, we will result with transformations like this. So we started with a square, and then we can transform it to rectangular to scale if we do not apply rotation. And we scale it along one axis, or we can change angles with affine transform. But still, for all these transforms, we have the common property that parallel lines are still parallel after the transformation, as you can see, for example, from this, the most affected figure. And finally, if we work with projective transform, the most flexible transform, and actually this is the transform behind the way to create images. And so here, actually, we cannot guarantee that parallel lines are still parallel. We cannot guarantee that we have the same angles, but we still have some properties. For example, the number of interactions or the order of contact. It means that if you have if your lines had a common point before transformation, then they will have a common point after the transformation. And well, these are parameters which are from one side, these parameters can be used to modify images, but also imagine that you have two images or two set of vectors, but we will work with images obviously. And then you will, sorry for, again, for some misunderstanding. So these operations are applied to vectors. If you work with images, we need to extract some vectors from the images, and then we can apply these transformations. So when I say we want to apply this to images, I mean that we need to extract something from image, some vectors, some points, or some lines, and then apply these transformations to lines, vectors. And my point is that, so if you have, say, a vector or a set of vectors and a transform, actually a matrix, then you can create a new set of vectors that just multiplying your vectors by this matrix. Or if you have two sets of vectors and you know that one-to-one correspondence, then you can try to solve the inverse problem. You can try to find the parameters of your transform. If you have two, two sets of vectors, corresponding vectors, then you can try to fit your transform, just to solve, again, inverse linear problem. And we will return to this important approach at the end of the lecture. But by now, we need to understand that we can apply linear transformation to images, and we can try to fit these transformations to achieve some properties we want to achieve. Now we can switch to half transform, and half transform, as I said, is a method to find lines in images. And before we proceed to the description of the algorithm, we can we can discuss the way to parameterize lines. And obviously, if we have two lines, so we have several points with known coordinates x and y, then, well, straight lines can be parameterized in this way. So we have one multiplier and as a free term. What is important is that we can switch from the original x-y space of our Euclidean space where our vectors live to a B space. So this is a space of different lines. So each point here gives us a line there. And vice versa, interestingly, a point here gives us a line here in a B space. And the reason is that if we have a point, we can draw several lines, right, which go through this point. And it means that we have several lines, and we can set a point for every line in AB space. And finally, actually, obviously, this is not a finite number of lines, and this is just an infinite number of lines we can draw through a point. So we'll result in a line here. Okay. And also we can use a different parameterization. So this is the most direct and simplest one. Or we can say that we use this way to parameterize our line. And here we have an angle, and for some reasons we have different angles. I'm sorry, within the formula and the image. But I hope that it's clear that we can use this parameterization, and we can simply divide these parts by SAN. So we will extract, here we have cotangents, and will be a different free term, but we can easily switch to this definition. So this is just a different parameterization of half transform, of a line. And now the goal is we have an image and we want to find lines, and okay, I have, it seems that one slide is missing here as well. Do I have an example? Yeah, I guess that we can return to the previous slides a little bit later, and we need to go through this one. So imagine that I have an image, and again, for simplicity here, we have say edges for, or some binary positive values for black lines, as we had for previous lectures, and we want to identify these lines. And the idea is that now, again, each line corresponds to a point in AB space, or in a row of theta space. And we need to somehow estimate the strength of every point in AB space, right? And then if we have a bright point in this AB space result, it means that we have a strong activation, a strong, suggestions that this line, this point actually corresponds to some line present in the image. And here we have originally, this is a very simple image with two lines. So we have two activations here. And the core question is that how can we estimate the strength of signal? So how can we validate the assumption that we have a line with parameters A, B in the original image? Before I proceed to the answer, I see that we have a question from Mohammed in the chat. Does it mean that sin theta equal to 1? No, actually, it doesn't mean. It's just a different parameterization. And I assume that this is not equal to 0. So that theta is not equal to 0. If we, for simplicity, ignore these cases, then we can say that we can this is not a non-zero number. Then we can simply divide by this number, and we will have this A will be equal to minus cotangents, right? If we switch from this parameterization to this one. And well, I guess that I can switch to the board. It will be easier. So we have this parameterization. Then again, for simplicity, we can assume that this is a non-zero, so theta is not equal to 0. And then we can switch to this representation plus so this is B, and this is A. Why is it important? Because this representation is a simple one, right? It's easier to understand that, well, we have a line with two parameters. But in some real scenarios, we have this parameterization, sorry. And I can show an example. For example, so now we want to plot a line, and then I guess that this is actually this missing slide. I'm sorry, I combined two different lectures and it seems that the order is not correct. Well, this image, actually, this one is a good example. So imagine that we have a binary image with just several activations. We have no lines, I mean, just lines here, but we can see that, for example, these 5 points, or 5 points, yeah, these 5 points are from one line. These 3 as well, right? And then we can try to we can try a different set of parameters, A and B. So each parameter in this grid, each point within this grid corresponds to a line. And then we plot a line which corresponds to these parameters, right? And this is the activations. How can we count activations? We just sum all the numbers for binary images, for example, we just count the number of pixels which have intersection with this line. And you see that for the majority of lines, so for the majority of points here, we have almost zero activation. It's non-zero just because here is intelligent algorithm is applied. So we have every line goes through at least one point. And then we can try to plot all the lines and count the activations, and then select the output, the set of parameters with the highest activation. And it seems, at least for me, that the best activation should be for this line, and I guess that this yellow square corresponds to this line. So the idea of the algorithm of the half transform is that we plot a lot of lines and then count the number of points, or the quality of fit in some sense. Imagine that we have a binary image with some edges, and we want to find lines within this image. Then we try all possible lines to fit all possible lines with all possible parameters, and then calculate the number of pixels, edge pixels, which intersect with every line. And then if we identify the direct line that we have these edges, I mean, this counting for every pixel, and the final number of, say, votes will be high. If we just intersect a couple of lines from original edges for one particular set of parameter A, B, in this case, the activation will be low, as we have here, right? These dark blue activations are low activations. And our goal is to just count all the numbers. And this can be done efficiently. So for two-dimensional space, there is an algorithm to count this in a fast way. So half transform allows us to convert from this actually binary image. It can be non-binary, but well, we just count not 0 and 1. We will count different. We will count corresponding numbers to that space, and here identify A/B parameters with the maximal activation. Actually, there is a different problem. In some cases, in some scenarios, we, instead of the original image and the goal to count intersections, we have a set of results of counting, and we want to restore the original image. And if we work in continuous domain, not in a discrete one, right, like we had in this example, in this case, this counting can be interpreted as integrating. So we have a line, we have a function, and we can interpret counting as the integral, one-dimensional integral for example, we have this line, so we have 0 or out of domain here, and then we need to integrate our function for x and y belongs to this line. So in our two example, we didn't integrate, we just count, because we have a finite function and finite image. Sometimes it can be also useful to solve an inverse problem. So we have a set of integrals or a set of sums for every direction, and then we want to restore the original function. As I said here, we have, well, actually every point here corresponds to a line here and vice versa. So these spaces are connected. And even if we work with not just counting just a very simple binary function, for example, for binary edges. If we work with some, well, complex function, we still can switch from this space back to that space. And the most common usage of this approach is computed tomography, or actually any type of tomography. And the physics behind it that we have a rotating X-ray tube with a set of sources, and we have some detectors to collect X-rays which goes through an object. It can be, well, human body or some other objects. And the idea behind that is that the density of the object can be described as F. And then if we have a set of particles, and some of them started from here, and then some of them will be stopped within a human body or the object. And the density of the object corresponds to the number of, to kind of opacity of this part of the object. And if we have a lot of integrals values, and we can estimate integral just comparing the number of particles here and here on the detector. And so the number of lacking particles are within the object. So we can in that sense, we can calculate the integral. And then we can try to transform, and here, this is a very nice explanation why this parameterization sometimes is a more useful approach. That's because here, this is a natural way to parameterize image, to parameterize our lines, because, well, we have different angles, right? We have rotating tube. And the math behind this transformation is called inverse Radon transform. I mean, if you have a set of integrals and you want to restore the original function. So at the end of the day, we want to understand what is inside the object. And so we want to estimate this function. Interesting that Radon transform and half transform, it seems that it were developed independently. So Radon transform was a mathematical transformation with functions, integrals, etc. And half transform was created as kind of an engineering approach to identify lines which corresponds to patterns with high activations. But actually, half transform can be considered as kind of an engineering approach to calculate a discrete Radon transform. So half obviously works with discrete images. As kind of a side note to well, maybe to discuss something real related to this image processing part before we will proceed to to the remaining parts of transform. I can mention that we I guess that I showed this part during the first lecture. It was a paper published in a joint conference on neural networks this year, and the goal was to remove these artifacts. And how we achieved this goal? We converted our image to the original so-called sinogram. So you may think that we apply half transform. So we calculated the integrals for different lines, and this is the result of these calculations. So this is, as you can see, we have some scene-like or scene-like patterns, and the parameterization is this one. So this is why we have these patterns, and these bright patterns corresponds to objects with high density. So for different lines, we have a high integral for lines which go through this bright pattern, and this is the result. You see that we have several lines here, and actually we want some of them related to the skull, so it's okay to have these high activations, and some of them, well, must be removed, which corresponds to this part of corrupted image. And we created an algorithm, a deep learning-based algorithm for inpainting. So we removed parts of this sinogram which corresponds to artificially generated object. So we started, actually this sinogram, this sinogram is just, well, the original sinogram of the brain. Then we generated artificially objects to simulate a real shape of these objects, calculated their sinograms. And then we say, well, we do not know nothing about these parts because these parts were corrupted by these high density objects. So we just cannot estimate, we cannot count the sum of we cannot count the integral just because all the particles were stopped here. So the detector receives nothing. And for such high density objects, well, we, due to the subsequent processing, we had these artifacts. And the idea was to, we know that for some parts of the sinogram, we cannot estimate the integral, I mean, from the original observations. But we can use the sinogram, and the assumption that, well, human tissues are in some sense continuous. So we can try to use information from the surrounding areas to restore the this missing part of the sinogram. So it cannot be, this was artificially added. So this was a fine sinogram. And the goal was to remove this, actually to restore or to inpaint. Just to remind you that we discussed inpainting as one of image processing problems. To inpaint these missing patterns using, well, some information from other lines, integrals from, so calculated integrals for other lines, and also some overall understanding of human anatomy using, well, again, a training set of samples. Then we restored this sinogram with some, well, still some artifacts. For example, as you can see here, this restoration is not ideal. For example, we have bright line here, oops, a bright line here, bright line here, and here it's somehow corrupted. So for these, and when we restore the original image, so apply, go back, so we apply an inverse transform to go back from sinogram to the image space. And you see that we have some artifacts, and then these artifacts were removed in this domain using just convolutional image-to-image convolutional network, and this is the result. And then this is a training procedure, and then we can apply the same procedure to a real image with artifacts. So we will not have training loops, then we will just detect these high density objects, estimate their sinograms, remove it from the image, restore sinogram, and then restore image. This is another another thought related to half transform. Actually, we just switch to a different space, and in our we have two parameterizations, right? This one were angles, as we had here, for example, or this straight line, but we can try to count, apply the same idea to count activations, for example, for binary image, as we have here. So we have edges created for this image, and then we want to fit some parametric function, and obviously this function, it can be circle or ellipse, and this one is ellipse, and ellipse can also be parameterized with some parameters, and then we can try to use the same logic. So for example, if we work with circles, we now have 3 parameters, and it means that we now have 3-dimensional space of different circles, and we can again repeat the procedure. We can try to go through all possible combinations within this 3-dimensional space. It's a discrete, right? Discrete space, and when we work with lines, we can assume that we just have the same number of A/B parameters as we had pixels in the original image. Well, for circular transform, we can limit the set of radius by some reasonable numbers, and also we can go through different different locations of with some predescribed step, and I've just observed that I close the chat, and is transformation objective? If we ignore some numerical issues, then yes, yeah. So we can go through, say, through this image to this one and back, but actually there are some numerical problems we related to, say, for example, linear algebra, and there are several methods and approaches how to resolve these issues. But from a mathematical point of view, it just objective. Well, yeah. So the idea that if we want to fit a circular transform, we can just go for different sets of regions and radiuses. The same is true for ellipses, but now we need to go through a whole set of 4 parameters in addition to coordinates of the center. We have 2 different axes and 2 different values for axes, but still we can repeat the procedure. The only drawback is that well, just greedy search in 4-dimensional space is even if you have an efficient algorithm to count the number of the number of intersections between your ellipse and the original object or the original set of edges. Even if you have an efficient algorithm, you still need to go through all possible combinations of parameters. And this is why the most common usage is linear half transform, just because you need to go through a 2-dimensional space, and it can be done, well, quite fast. As for circular, it sometimes can be used. Ellipses, I guess that's the only way to use it in some toy exercises, but just because, or if you have good a priori assumptions on, say, on position of your ellipse or on a radius, or so if you can reduce the dimensionality of your search, then, well, ellipses can be also fitted. And this particular one is from scikit-image tutorial, and we had an example with half transform to detect, for example, it can be used to detect road signs, right? We have road signs which are usually can be represented as circles if we do not take into account perspective. And we can try to use circular half transform to fit road signs. And we had this exercise last year, and I hope that we'll have time to do it in this year as well. Yeah, so we've already discussed this idea that we want to draw all the lines and just count the number of intersections, and then it will give us the 2 points with the highest activations. And this is the same illustration of this interactive process. And, well, this is an example of applied transformations, of applied half transform to a set of edges to identify lines. And again, you can see, this is a very nice example. I mentioned railways, but I guess this one is fine as well. We have several actually parallel lines in this corridor, and you can clearly see that we have this vanishing point here. All the lines, parallel lines from the image have a common point here. Okay, so I'm sorry that well, slides were in slightly different order than it should be. I hope that we will go through the practical exercise. We have a really nice exercise for this part, so it will be released today, and then we will discuss it on Friday. I hope that this will help us to understand the at least practical aspects of half transform. But basically, we just counts. We just want to estimate the integral, or as we work in discrete space, we just want to calculate the sum for every line. A question from Leonid. The line representation does help to train nets. I mean, why did you choose to in-plane line representation instead of scans? Well, it's a good question, and the answer is that we try different approaches, and this is just kind of an experimental result. Then this procedure works better than we can work. Actually, this is a quite established topic in medical image processing, and it's called metal artifact reduction, this part MAR. And all the methods can be split into two parts. Some of them work in sinogram domain, some of them work in the original image domain. And we found out that it's better to use both domains. And the intuition of applying in painting to this part is that as you can see here from in the original domain, if we have artifacts, we have, well, quite low set of pixels, I mean neighborhood pixels, which allows us to reconstruct some information about these parts. And in this case, we will mainly use some a priori anatomical knowledge. For example, that we have some brain tissues here and do not have skull here. So again, this is just intuition and can be to explain the results of our computational experiments. And if we work in sinogram, it seems that we have more information to restore these corrupted parts. It's because it's, well, more less size, less area. Well, this is the only way I can explain these results. Yeah, and with neural networks, it's possible to use this approach. And we wrote this paper in 2019, and then a couple of papers were also released with, they use slightly different approaches, but, well, they also demonstrated that working in both domains is better than select just one. Okay, then the last ingredient is so-called Ranzak algorithm. Before we go through the formal definition, I propose to go through this this example. So what is the problem when you try to again, the right order should be this one. This is the practical exercise, and the goal is to combine three approaches. So we have this image, and as we know, we have obviously we have parallel lines for main Caltech building related to the orientation of these bars. And we have a vanishing point there somewhere. And the goal is to transform this image to that image. Not exactly this one, obviously, because, well, it's not possible to create exactly this one, but we can still to emulate the view from above. So we can start with this image and emulate or somehow normalize the image to obtain similar representation similar to this one. And how can we do this? First, we can start with edges, and obviously we'll have a lot of edges here, right? And then some of these, then we can try to find lines. We know that we want to convert this image to that image. So we know we need to find these parallel lines to estimate the parameters of projective transform, which connects these two images. So we want to, we believe that there is a projective transform which was applied to this image to obtain this one, right? And so we can fit, we can try to fit, and this is a linear transform, and we can try to fit an inverse transform. Again, this is projective transform to switch back from this view to that view. And to find parameters of the projective transform, we need to identify lines which must be parallel. Right? We want to start with these lines and then make them parallel. So to find that transform, yeah, well, I guess it's clear. And basically the steps are, first we need to find edges, for example, using k-name. Then we need to identify lines using half transform. And then using these lines, we can try to switch to this representation. And it means that we need to fit the parameters of projective transform, right? We have the matrix of parameters, and we can try to pose this problem as an optimization one. We can try to say, when we say that we want to create, we can define these lines on this image, and then we can try to fix, to change parameters in order to minimize, for example, mean square distance. And the problem is that in addition to actually parallel lines with a common vanishing point, we will also have other lines for sure. For example, we will have this line. This is an edge, and likely this line will be detected as well. Or, for example, some lines related to roads or, well, some other parts of the image. And it means if we will try to use these lines in our optimization problem as well, it means that we will, actually this is an outlier. This should be removed from our optimization problem. And the core question is how can we remove outliers? So we know that we have a dependency between two sets of points or vectors, and some of pairs, some of the information is just wrong. So we do not take this information into account when we try to fit our transformation, our linear transformation. And the question is, how can we do it? And the answer is that we can use Ranzak algorithm, and well, there are other options, but Ranzak is efficient and quite fast, though it's random. So what is the idea? Imagine that we have a really simple problem. We want to just solve a linear regression. So we know pairs X and Y, and we know that Y is a linear dependency. Again, A multiplied by X plus B. And we have some outliers. So we can estimate that likely these 4 points and these 2 are outliers, and we need to fit the line using these points only. And you see that there is a noise, and any real image in after real Kenny and real half, you will have some noise in your lines for sure. And the question is, how can we fit the line? The possible answer is that we can just fit linear regression. We know that we have pairs X and Y, and in this case, X and Y is just numbers. And we know the dependency, we know the parametric form, that Y is A multiplied by X plus B. And the problem is that if we will try to fit, for example, to fit our the model using MSE, mean squared error, in this case, these outliers will contribute significantly to MSE, and we will find, well, something like this line, or I don't know, yeah, this line, for example, which is not correct. So we need to somehow remove these outliers. And Ranzak works in the following way. It starts with a small set of points, random points. These points are selected randomly, and these are green points for the first illustration. Then it uses these 2 points to fit a line. So the assumption is that if we select a small subset randomly, then at some point we will find 2 points from real distribution from without outliers, and we need to somehow validate our assumption. So to understand that these 2 points are the small set of points is a good one. And we use these points to fit a line or fit another transform. What is good about Ranzak is that you can use it for linear regression, you can use it to fit parameters of projective transform. It doesn't matter. The only thing you need is that you have some fit option to create a transformation, and score option to estimate the quality of fit for new points. And here, fit is just to draw a line, and score is to estimate the distance from point to this line. And then we have a threshold T, and if the score, so again, for this simple linear regression case, it's just the distance from the point to the line. If this distance is smaller than threshold, we say, okay, these are inliers. So in addition to 2 original points, we also have 4 inliers. And then we can try to find the, uh, the line with the largest number of inliers. Just randomly repeat the procedure, the first, these three steps. Randomly select 2 points, then fit a line, and then find the number of inliers. And you see that here we have only 6 inliers, taking into account the original 2 points. Here we have 11. So this line seems to be a better alternative than this one. For these 2 points, we have only 4 because it was fitted using an outlier. And finally, when we repeat this procedure several times, then we have the best line with 14 inliers, and actually it corresponds to the intuition that we need to remove these 6 points. The actual algorithm is slightly more complex. For example, we need to process cases with equal number of inliers, and in this case we can calculate the average score for every point, for every inlier, and then select the line with better score. So this is a very simple algorithm, and the only limitation is that it's a random one, and you need to select your parameters carefully, taking into account the your expectation about the number of outliers. So in other words, you need to select the number of points. Here we have only 2, the number of points with care. And the second comment is that this is a random procedure. So you repeat this procedure, random procedure, many times. And sometimes if you have, so for example, if you have a lot of outliers, in this case, well, you cannot guarantee that at the end you will have the right solution. Maybe you won't find any random set of points and where all points are inliers. Well, so this is a limitation, but from practical point of view, usually this is a quite robust algorithm and to solve the problem. And in particular, we can use it to solve the above mentioned problem with when we want to fit our transform, we need to remove outliers first, and it can be done with Ranzak. Yeah, and this is well, another example is that Ranzak can also be used for regression, but well, just if you are familiar with scikit-learn and regression, and many of you participated in the Introduction to Data Science course, that so I guess that you are familiar. So the example is just a different one, is that now we want to fit a non-linear basis of functions, and we have actually a nice black dots, just data points. We have a nice function here, and we have several outliers. And if we just apply least square estimation, then you will have these wrong estimations. Well, it's more or less clear. Or we can use some robust algorithms, for example, Huber regression and Ranzak, and in this case, we will have smaller errors. And as I said, the core, so if we want to solve a linear regression problem, actually this is just a linear regression within a linear basis, but at the end of the day, it's a linear problem. Then we can use different approaches. Instead of this random sampling, we can, for example, switch from L2 norm to L1 norm. So instead of minimizing MSE, we can minimize L1 norm. And in this case, the contribution of outliers won't be as significant as for L2. But Ransack, again, needs only a way to fit something and then use calculate scores for every point using this fitted something. For example, it can be line and distance to the line. But we can simply modify Ransack. We can say that we will use not the distance, but just the difference in x coordinate or an y coordinate. If we, for some reasons, need this for our application. So Ransack is highly customizable. Yeah, if points are selected randomly, how will we be sure that we can reach an optimal line? Actually, we cannot be sure that we find the best possible line. But there are some validations within the algorithm. In particular, when we repeat the procedure, for example, here we repeat the procedure 4 times, then we estimated this line using just 2 points, and finally we decided that this is the optimal line, and then we repeat the line using all inliers. So it allows us to it not guarantee, it does not guarantee that we find the optimal line, but the last step allows us to find a more robust representation than it was fitted just using 2 points, or so say a small set of points. So we suppose that we find all inliers, or at least the majority of inliers. We can lose some of inliers if this original line wasn't fitted in a really good way or close to optimal. But then we can refit, and this estimation will be more robust. Pictures look like SVM explanation. Well, it's yeah, it's similar to SVM, because yeah, we have kind of yeah, it's similar to SVM. I agree, but we do not have different classes here. But this part with the distance to the line is similar to SVM. But there we want to find a line to separate 2 classes, and here instead we want to find a line to to identify parametric equation for pairs of points, or it can be again vectors. Okay, so we have we spent 1.5 hours. I propose to have say 15 minutes break. Then we will so we'll start our seminar part at 10:50, and the first part will be about contours in OpenCV, and then Boris will explain you his solution. Will share his solution to template matching for Skoltech lamps. Thanks, and we will come back in 15 minutes.